Welcome to this explainer. Today, we're going to unpack a completely fascinating new hypothesis for hunting hidden objects in our universe. We're specifically zeroing in on the search for something you've probably heard a lot about, the mysterious Planet 9. It's this massive cosmic mystery, and today we're looking at a brilliant new map that might actually help us finally solve it.
So right off the bat, we run into a simple but honestly massive puzzle that has troubled astronomers for centuries. How do you find a giant planet hiding in the dark, freezing edges of our solar system when it doesn't even make its own light?
To answer that, we're going to cover the cosmic search problem, the new IOPI framework solution, the 3 priority lanes for Planet 9, validation mechanisms, how to falsify the index, and finally the real-world implications of all this.
Okay, starting with Section 1, the cosmic search problem, and why space is just so incredibly hard to search.
Our existing understanding of the problem is pretty straightforward. Space is, well, it's mind-bogglingly huge, and telescope time, that is incredibly limited and super expensive. When our math and our models show that something massive is pulling on objects out at the edge of the solar system, we know something is out there. But blindly pointing a telescope into the night sky? That's literally like looking for your lost keys in a giant pitch-black warehouse using a tiny little laser pointer. You could search for years and find absolutely nothing simply because you were looking, say, an inch too far to the left.
Moving to Section 2, the IOPI framework solution, a much smarter way to look.
This brings us to a really groundbreaking hypothesis proposed by researcher, inventor, and author Kevin L. Brown. It's called the Informational Observation Pressure Index, or IOPI for short. You can kind of think of IOPI as the ultimate search engine ranking for the universe. Instead of just guessing, it mathematically ranks exactly where astronomers should look next, based on where we can learn the absolute most. Going back to our analogy, it helps us figure out exactly where the light from the window hits the floor, so it's way easier to spot those lost keys.
Now, what's really interesting about this is how IOPI actually works. It takes all these different clues that usually exist in their own separate scientific bubbles and puts them together. It looks at survey gaps, meaning the places we just haven't searched yet. It looks at candidate strength, so how good are our current clues? It factors in temporal visibility. Basically, is it actually a good time of year to see this part of the sky? And it checks instrument feasibility, which just means, do we even have the right telescope for the job? IOPI takes all of that and turns it into one single ranked score to guide our telescopes.
Section 3. Planet 9 Priority Lanes. This is where we apply the index.
The absolutely crucial point here is how this applies to our biggest local mystery, the hunt for Planet 9. Brown's framework outlines 3 strict priority lanes for observation. These lanes cut out all the guesswork, telling us exactly where to point our instruments first, second, and third. The absolute highest priority, Lane 1, is directly following up on existing infrared clues. See, we already have some blurry spots in old telescope data that glow in infrared light. IOPI basically says, hey, stop searching randomly, point our best telescopes right at those specific spots, and test for what scientists call cross-epoch motion. In everyday terms, that just means taking pictures over multiple nights to see if those spots are actually moving across the sky. If they move, well, they might just be our planet. If they don't, they're just background noise. Now, what if Lane 1 doesn't pan out, and those spots are just noise? The index tells us exactly where to go next. Lane 2 focuses on what the models call the remaining dynamical space. These are the really faint, unsearched zones that our optical telescopes haven't fully ruled out yet. They're areas where the math says a planet could be, but the object would be incredibly dim. IOPI ranks these zones, so we search the most mathematically likely dark spots first. And if we still come up empty, well, Lane 3 is reserved for completely different alternative models of unseen planets. The IOPI framework keeps this strictly separated from the first 2 lanes. And this is so important because it ensures our data doesn't get messy. We test one specific idea completely, actually scratch that, we test it exhaustively, before we mix it up with another idea.
On to Section 4, validation test mechanisms. How do we actually know if this works?
In science, success isn't just about finding the prize, right? Success is about reducing uncertainty. These test mechanisms prove IOPI works if it leads to one of 4 things. First is discovery. Obviously, finding Planet 9 is a massive win. But the second is candidate elimination. Ruling out a false lead is also a huge success because it shrinks the haystack. Third is model revision, which means updating our mathematical maps with new data. And fourth is search space reorganization, narrowing the hunt for the next time we use the telescope. If IOPI does any of these efficiently, the framework is a success.
Section 5, How to Falsify IOP. This is the ultimate test.
For any hypothesis to be good science, it has to have clear falsification parameters, meaning there has to be a way to prove it wrong. For Kevin L. Brown's IOPI, those parameters are incredibly clear. If we repeatedly point our telescopes exactly where IOPI gives a high score and we learn absolutely nothing new, no discovery, no ruled out candidates, no updated maps, then our uncertainty hasn't dropped at all. If that happens, the entire IOPI framework fails. It's a really bold, testable claim.
Finally, Section 6, Real-World Implications. Let's look beyond Planet 9. The real-world implications of Kevin L. Brown's hypothesis are actually huge. This isn't just about one missing planet. This exact same index can be transferred to hunt for dangerous, hidden asteroids that might cross Earth's path. It can be used to locate distant exoplanets orbiting other stars. And practically speaking, it helps scientific institutions save millions of dollars. By using IOPI, they can book scarce telescope time much more efficiently, getting way more bang for their buck by only looking where they'll learn the most.
Researcher and author Kevin L. Brown states the core purpose of the index is not to maximize excitement, it is to maximize information gain. That quote just perfectly summarizes the shift in modern astronomy. We're moving away from simply guessing where the most exciting things might be to mathematically calculating where we can learn the absolute most, step by step, observation by observation.
Which leaves us with this final thought. With the IOP framework showing us exactly where to shine our flashlights next to reduce uncertainty, we really have to ask, if we finally have the perfect map for the dark, what other cosmic mysteries are about to be solved? Thank you so much for joining me for this explainer. Keep looking up, and I'll catch you next time.